So we'll start talking about Markov Chain Monte Carlo, MCMC for short. We'll change notations a little bit. We're going to use D for the data instead of Y now, and we'll keep using theta to denote parameters of the model. So let's do a quick motivating example. Let's say we want to study the shuffles of a standard deck of cards, and we want to study some type of summary statistics of those shuffles. And the naive approach to study those shuffles is to enumerate all possible perturbations of this deck of cards. And in a standard deck of 52, 52 factorial is the number of possible shuffles. And if you calculate this number, it's actually around 10 to the power 68. And it is slightly less than the number of particles in the universe, which is 10 to the power 80. So it's simply impossible even to enumerate all of them and store this in the computer. And instead of doing this naive approach, we can do what is called Markov Chain Monte Carlo. So we can generate card shuffles, random samples of the card shuffles. And we can generate those random samples by using a simple Markov Chain approach. So here's how it works. Let's say you take an unshuffled deck of cards, and then you take the top card and then generate number between 1 and 52, and it will be the position of this card. So let's say generated 34. So you take card from the top and put it into position 34. And you keep doing this. So every single time you take the top card, you generate a random position in the deck and you put this card into this new position. And after you do it for several hundred times, you actually will get a shuffled deck of cards. So what is Markov chain here? Markov chain here is the intermediate shuffles. So every time you take the top card and put it in a different position, what you do a Markov chain step, meaning that all of those shuffles will only have the top card that is different, and they will be very similar. But if you do those Markov chains, if you keep doing this Markov chain for long enough, then in the end you actually will have a shuffle that is purely random shuffle. So if you take unshuffled deck of cards, you do it for 200 times this top card replacement. And you do the same thing with another deck of cards. So you take the top card and you replace and put it in a different position. And you also do it for 200 times. And then if you take those two decks shuffled in this way, they won't look any similar. So there's going to be no correlation. Even though there was a correlation in intermediate perturbations, so each deck of cards in the sequence of 200 is very similar to the previous one. But if you do it long enough, the similarity actually disappears. So that's the basic idea between Markov chain Monte Carlo. You want to come up with this Markov chain approach with a simple way of generating a sample given your current state of the deck of cards. And in our case, it was taking the top and putting into a different position, randomly generated. So that if you keep doing those simple perturbations at the many times, and the end you will have a perturbation which actually is not correlated to another deck of cards that was shuffled in a similar way. So another example of using Markov chain simulations is to calculate approximations of expectations, something you probably have seen before. So we have some function of theta and x, and it can be a neural network, theta the parameters of the neural network, and x is the input. And you want to calculate an expectation over this function, over the output of this function. And so what you can do, you can generate G samples from theta and from x, and then you just calculate the value of the function for those G samples, and then you average out those values, and essentially this will be the approximation to the expectation. In this case, and as any other case, expectation is just an integral, right? So in more general case, we're going to be talking about Metropolis Hasting algorithm that allows us to generate those Markov chains that eventually converge to generate samples from the target distribution. And we'll start by talking about random walks and graphs. So let's say you have a graph that is shown here. It has 7 nodes. and there is a series of connections between the nodes called links or edges. And we do a random walk on this graph, and random walk is governed by these matrix of transitions. So the matrix tells us that we have zeros on the diagonal, means we never go back to the same state on the next time step. So if we're at state 1, we in the next time step will be at some different state. And so let's take this one. So if we're at state let's take this row. So from node 1, there is 50% chance we're gonna move to node 2 and 50% chance we're gonna move to node 3. And so 0.5 here and 0.5 here. So that's what the transition probability matrix tells us. And now what we're interested in what is called a stationary probability distribution of a graph. So imagine you do this random walk and you do it for long enough so that when you calculate average time that you visited each node, so average, or just the number average times you visited node I, which is just the number of visits to node I divided by the n, and n is the total number of random steps you did on the graph, random walk steps, number of random walk steps. Okay, so at some point you'll see that this number becomes more or less stationary, meaning it doesn't change. And this number, the number of visits divided by the total number of random walks, is what is called stationary probability over this set of nodes of this random graph. And in this case, we actually can analytically calculate the stationary probability. It's going to be this vector, and it's going to be zeros everywhere but the state 6 and 7. And if you look carefully enough, the reason for that is because the transition matrix tells us if we are on node 6, then there is 100% chance that we're going to end up in the node 7. So from node 6 to node 7, probability of moving 1. And vice versa, if you are in node 7, there is 100% chance that you're gonna move to node 6. So this is also 1. Meaning that the moment you walk into the node 7 or node 6, you'll just keep bouncing between those two nodes back and forth. So this is somewhat degenerate case, but it is what it is, and it's simple to imagine why this happens. And it also can be calculated analytically. And in the case of discrete random walks, this is just the second eigenvector, or the eigenvector that corresponds to the second largest eigenvalue of this transition matrix. The first eigenvalue is always 1. And this is essentially the algorithm or the idea behind Google search, at least the search that has been used for a very long time, from the 1998. The algorithm is called PageRank, and the PageRank essentially calculates those stationary probabilities for web pages. And in case of the Google search, each web page represents a node of the graph, and the link between one node to another node is represented by an URL. So if my web page has a URL link to some other web page, then on this web graph, our two pages will be connected. There's going to be an arrow from my web page to this arrow, the page I'm referring to. And so the Google PageRank essentially takes this matrix of the transitions between pages and calculates the second eigen vector. It uses the power method to do that, and this gives you the ranking, which sides are more popular. And the Google, of course, search algorithm conditions it on the search query, but the basic idea is very similar to what we did with this graph. So now the question is, how do we apply this idea of random walk on the graph and connect it to what we need to do? You remember our goal is that we want to generate a sample of a p of theta given data. So we would like to use this Markov chain approach. It means that we generate samples, from this distribution. So what we need to do, we need to design a Markov chain. So it's a sequence of samples from this space of theta, sequence of samples theta. So that if we keep doing this, the same idea as we did with card shuffling, we just do some simple perturbations to the theta. So we start with some theta and we do some perturbations to it, so we get the next one, and we keep doing those perturbations. And if we do them long enough, then after a certain amount of steps, we actually have a true random sample from this distribution of interest. And Metropolis Testing does it in the following way. So we start by drawing what we call theta prime from some, let me zoom into this so you can see a little better, from some proposal distribution. And so we're going to call it p of theta prime given theta g. So theta g is our current value of theta. So you remember in Markov chain, we take the current value and we move to the next one. And we keep doing this. And so in the next step, what is the new value of the parameter theta becomes the current one, and we move from this one to the next one. So so we have some proposal distribution. So we sample some theta prime. And then what we do, we accept this theta prime with this probability alpha, which is just given by this formula. So it's a minima, and it's minima between 1 because we don't want probability to be more than 1, so it's always below 1, and this ratio here. And this ratio here, if you look carefully, actually pi of theta is our target distribution here. So in the case of a neural network, that's going to be the posterior p of theta given the data. And if you look at what Metropolis Hasting algorithm requires, it actually requires the ratio of this target distribution calculated at value theta prime and theta g, which is our current one. And if you remember, the hardest part of doing the Bayesian inference was to calculate this total distribution over data, which is our that's where the integral arises. And actually, if you take the ratio, so let's say our pi of theta equals to p of theta given data, and you remember that it's p of theta given data times the prior p of theta divided by p of data. So the p of data is the hard part, right? And now let's calculate, so pi of theta prime is just pi of theta prime given data. And it's equal to pi of data given theta prime, pi of theta divided by p of data. So the nice part about this ratio is that when you take pi of theta prime and you divide it by of theta, the total probability p of data actually disappears. So what you have is pi of theta prime given data times the prior pi of theta prime divided by of theta given data times the prior pi of theta. So there's no this probability of data anymore. We don't need to really calculate this integral. So this one is easy to calculate. And in this class, we're gonna skip the proof of this fact. But what will happen if you keep doing that? So you start with some value theta g, and you have this proposal distribution that proposes that you move to this new location theta prime, and then you decide whether you keep this theta prime or you do not keep this theta prime by looking at this ratio. So you might go back to your previous value, or you might actually stay at this new value. And then you keep doing that. And if you keep doing this for long enough, then this sequence of the status that you generate from this process is actually going to be the samples from your target distribution. Here's a quick demonstration of the Metropolis Hasting algorithm. So we just try to generate random samples from normal distribution. Our posterior is normal. So our pi of theta, which is just our posterior of theta given data, is normal. It's the simplest case, of course, that just for the sake of visualization, for the sake of showing things, this is not practical. And what you see here in the green, green are the samples that were accepted, and the red the samples that were rejected. So let's look at this case, for example. So we moved from this point to this point. So that was our theta g, and that was our theta prime. And what happens under this posterior model, if you calculate the ratio of, in this specific case, the pi of theta prime given pi of theta g is a small number. Why it is a small number? Well, because let's say that's the mean of that distribution that we're trying to study. And in the normal, you remember the further you are away from the mean, the lower the value of the density, and in normal distribution, this decay is exponential. So the p of theta prime is a small number, and p of theta g is relatively large number, right? Large number. So the ratio of a small and large number is a small number, and you remember that you calculate the probability of rejection is proportional to this ratio. So it means that the probability of rejection in this case is high. And that's the simple idea. So you essentially, the Metropolis Hasting algorithm tries to spend more time in the areas of high density compared to the areas of low density. Although once in a while you will have this move, like move here, right? So from this point to this point, or move from this point to this point. So this is green, means it was accepted. You went from here to here. You went from region of high density to the region of low density, and although you generate the low probability or high probability of rejection, you still do not reject. So you keep the sample. So once in a while it happens, and so you still generate once in a while samples outside of this area of high density. And another modification of Markov Chain Monte Carlo is what is called the Gibbs Sampler. Gibbs Sampler, we're going to consider a simple case when our parameter theta has just two values, theta 1 and theta 2. And theta 1 and theta 2 can be blocks of the variable, so it can be single variable. Doesn't really matter, but we somehow split our variables into two parts, theta 1 and theta 2 part. And then in Gibbs Sampler, what we do, we have to have two conditional distributions when we split it in two parts. So the first distribution is the probability of theta 1 given theta 2. And the second one is probability of theta 2 given theta 1. And we just at every step of Gibbs sampling, we sample from both of them. So you take some current value of your parameter theta, then you take the second part of it, theta 2g, and you sample from theta 1 conditional theta 2g. And then in the next step of Gibbs sampler, you sample theta 2 given that theta 1 g plus 1. And if you keep doing this long enough, again, you'll generate a sample from the target distribution. Again, we're not going to go through details in proving that, but this procedure works. And typically, it is more it's preferable to use Gibbs Sampler compared to Metropolis Testing. It converges faster. However, Gibbs Sampler has a disadvantage. You need to know those conditional distribution, and typically you have to do some type of algebraic calculation. So you need to figure out those conditionals. And again, in a general case, it's relatively hard to calculate those conditional distributions. There are some specific cases where it can be done, and when it can be done, Gibbs sampling is very effective. But in the case of neural networks, for example, we cannot calculate those conditionals. And in case of neural networks, we are to use Metropolis Hasting algorithms to calculate the posteriors.